Hello everyone, welcome to the last lecture of our short course. In today's video we will dive into the concept of Mendelian randomization. We will explore how Mendelian randomization is used to infer causality, starting with its introduction and core theory, followed by a discussion of applications and key challenges in this powerful approach. So let's dive in. Mendelian randomization, or MR in short, is a powerful approach for causal inference, allowing us to access causal relationships using genetic variants as tools. In observational studies, confounding factors or reverse causation can obscure true causal effects. And MR helps address these challenges by leveraging the random allocation of genetic variants at conception. To understand MR better, let's compare it to randomized trials, or RT in short. Just like randomized trials use randomization argument to control for confounding, MR uses the principle of genetic randomization. During meiosis, genetic variants are inherited randomly and are independent of environmental factors. This provides a natural way to correct for confounding in observational studies. I will talk about this in the couple of following slides in more detail. But MR is also practical and overcome limitations of randomized trials, which again I will explain in the next slides in detail. But in summary, MR combines the rigor of randomized trials with the flexibility of observational studies, making it an invaluable tool for evaluating causal relationships in modern research. So randomized trials are the gold standard for causal inference. However, they have often limitations. They can be costly, they can be time-consuming, or even unethical. MR has an advantage over randomized trials because it offers a practical alternative to address scenarios where traditional randomized trials are either infeasible or unethical. For example, we cannot randomize people to smoke cigarettes or adopt a high-fat diet, but MR can provide insights into the causal effects of such exposures on disease outcomes. The figure on the right shows how these two are related. Because of the limitations of randomized trials and MR being based on the same concept with the randomized trials, MR become a practical solution for causal inference and is widely being used in the literature. And as you can see, the only thing that MR changes is the alteration in the randomized step. Because of this randomization, the confounding factors are being controlled. Now let's dive into the core logic and theory of Mendelian randomization. On the left of the slides, you will see the core logic behind MR, which is essentially an instrumental variable analysis, or in short IV, where genetic variants serve as instrumental variables. This concept was introduced by David Smith and Ibrahim in 2003. And the main idea is that if you are interested in estimating the causal effect of X, which is the exposure, on Y, which is the outcome, in the presence of confounders, which we represent with U, which are affecting both X and Y, you can use an instrumental variable IV to bypass the confounding. And to be valid, the IV must satisfy three conditions, which are outlined in box 2. In the middle of slide. So basically, one is relevance. So the IV must be associated with the exposure. Two is independence or exchangeability, which indicates that there must be no confounders between IV and outcome Y. And three is exclusion restriction. The IV must influence Y only through X, meaning that it should not affect Y via any other pathway or trait that influences Y. It's important to note that while condition 1 can be formally tested using statistical methods, condition 2 and condition 3 can only be disproven and not proven. So this is a key limitation of MR studies. On the right side of the slide, there's an example comparing randomized trials and MR for estimating the effect of lowering C-reactive protein on systolic blood pressure. This example basically highlights the practicality of MR compared to RTs, because we can use a genetic variant associated with lower CRP, which can be found by GWAS, and we can just run the Mendelian randomization, which is much easier to compare to the randomized trials. Now, based on the assumptions of MR, we can estimate the effect of an exposure X on an outcome Y using various methods. And let me walk you through two commonly used approaches. One is a two-stage least square, or 2SLS estimation, which is based on two steps. And on step 1, you consider the model between G and X, and you found the slope between them. So you found the effect of G on X, and then you compute the predicted exposure value. And then use this predicted exposure value as an independent variable in a model with the outcome Y. And the slope of this model is enabling us to estimate the causal effect of X on Y. And this estimate is free from confounding due to the MR assumptions, specifically assumptions 2 and 3. Now, the second method is based on something called Wald estimations. And Wald estimation method directly calculates the causal effect of X on Y using the association between the genetic instrument G and X and G and Y. So it looks into this fraction, this ratio. And this is particularly efficient because these associations are often pre-computed and available in GWAS summary statistic catalogs, making it super easy and super convenient to retrieve and analyze. I should also add that the Wald approach works both for single instruments, that is using a single SNP as your instrumental variable, or even multiple instruments, that is using multiple SNPs. And using multiple instruments often improves the robustness and the precision of the causal estimates. But both methods are powerful tools. Depending on whether a single SNP is good enough to explain the effect on the exposure, on the effect of the instrumental variable on the exposure, or if the trait is super polygenic and you need multiple instruments to add the effect of instrumental variable on the exposure. Lastly, both two-stage least square methods and the Wald estimation methods are powerful for causal inference in MR. And in the next couple of slides, I will be talking about the applications and the key limitations of MR. So there are many applications of MR that I have taken from a table from David Smith and Gibran Hermani's paper. This is from 2014, but you can see that there are many different uses of MR, and you can even find even more in the literature. So I will not go over this, but there are many clinical and different kind of applications of MR. And in the last slide, I will only be talking about the key challenges in MR. There are several key challenges and limitations associated with MR, which are critical to consider when interpreting the results. Well, the first one is the assumptions. The condition 2 and condition 3, it cannot be proven, but only disproven. And we know that MR relies on 3 assumptions for its validity, and these are essential. The second key challenge is the weak instrumental bias. MR requires strong instruments, genetic variants that are strongly associated with the exposure, and if the instruments are weak, they lead to low statistical power and biased estimates, especially in small sample sizes. This issue is commonly referred as the weak instrument bias. And to avoid this, usually instead of using single instrument, you used multiple instrument, just like in the Wald estimation. The another challenge is the pleiotropy, which means that genetic variants influencing multiple diseases or traits. And there are many different types of pleiotropy. I have taken a figure from a paper, review paper in 2023. This is a very good review paper of Mendelian randomization. Excuse me. And as you can see in this figure, there are different types of pleiotropy that we can encounter, and these require careful modeling. Each of these requires a careful modeling to ensure that the pleiotropy is not causing a challenge or bias in MR estimations. The fourth is the population structure, which is basically differences in ancestry or population structure can act as a confounder, just like in GWAS. For example, genetic variants may be associated with both the exposure and the outcome due to shared ancestry, rather than just the causal relationship. So proper adjustments for stratification are critical for avoiding any biased results. And lastly, the complexity of causal pathways. MR assumes a relatively simple causal pathway between standard MR assumes a relatively simple causal pathway between the genetic instrument and the exposure and the outcome. However, in reality, there could be often multiple pathways which can introduce bias, again, if not adequately modeled. These challenges highlight the importance of careful study design and robust sensitivity analysis, as well as advanced statistical techniques to ensure reliable MR estimates. So this brings us at the end of the short course. I would like to sincerely thank you for joining me on this journey, and I hope you found the materials engaging and gained a solid understanding of the fundamental concepts we covered. And if you have any questions or comments, please feel free to share them in the comment section below or reach out to me directly via email. I would love to hear your thoughts and help with any clarifications. Thank you again, and I wish you all the best in your continued learning. Bye.